Tonight, you flip a switch. Power flows through the wall, through the wires, through the transformer humming quietly outside your window. And light fills the room. You don't think about it. Nobody does. But here is a question almost no one thinks to ask. What if that power wasn't alternating? What if it was direct current, steady, flat, unchanging? The transformer would die. Not slowly, not eventually, almost immediately. And the reason why reveals something profound about the nature of electricity itself. Something that was fought over, lied about, and nearly buried in one of the most ruthless corporate wars in history. To understand the death, you first have to understand the life. You have to understand what a transformer actually is before you can understand why DC destroys it. At its heart, a transformer is not a device that moves electricity. It is a device that moves change. Two coils of wire, one iron core connecting them. No gears, no motors, no moving parts of any kind. That is the entire machine. And somehow, this simple arrangement can take 11,000 volts coming in from a power line and deliver 230 volts safely to your kitchen. The first coil, the primary, receives alternating current from the power grid. That current creates a magnetic field inside the iron core. But here is the critical word, the word that everything else depends on: alternating. The current is not steady. It does not flow in one direction and stay there. It rises, peaks, falls, crosses zero, reverses, goes negative, peaks again in the opposite direction, returns to zero, and does this again. In India, it does this 50 times every second. In America, 60 times. Over and over endlessly, for as long as the grid is alive. Every time that current changes direction, the magnetic field inside the iron core changes direction with it. And every time the magnetic field changes, every single cycle, something remarkable happens. That changing magnetic field reaches across the iron core and induces a voltage in the second coil, the secondary coil, without any direct electrical connection between the two wires. No wire touches, no current physically crosses from one coil to the other. And yet, voltage appears in the secondary as surely as if you had connected it directly to the source. This is electromagnetic induction. Michael Faraday discovered it in 1831 in a London laboratory. He took a coil of wire, moved a bar magnet through it, and watched a current appear, created from nothing but motion and magnetism. No battery, no generator, just change. Faraday's law, as it was formalized, states this with mathematical precision. The voltage induced in a coil is directly proportional to the rate of change of the magnetic flux passing through it. Rate of change. Those three words are everything. Not the size of the magnetic field, not the strength of the current, not the material of the wire or the shape of the core. The rate at which the magnetic field is changing. A C current changes constantly. 50 or 60 times per second, it is always in the middle of changing. Rising or falling or reversing. Which means the magnetic field inside the core is always changing. Which means the rate of change is always non-zero. Which means voltage is always being induced in the secondary coil. The transformer functions. It steps voltage up or down depending on the ratio of turns between the two coils. It does this with extraordinary efficiency. Modern power transformers operate at efficiencies above 98%. Almost no energy is wasted. Now apply DC. Connect a battery to the primary coil. Current flows in. A magnetic field builds up inside the iron core, and then stops building. The field is there. It is real. It is measurable. But it is not changing. A DC source pushes current in one direction only. Steady, flat, unwavering. The magnetic field inside the core reaches its maximum value determined by the current level and sits there, perfectly still. And because it is not changing, Faraday's law produces exactly zero induced voltage in the secondary coil. Zero. Not a little, not reduced. Zero. The transformer does not transform. The secondary sees nothing. No power crosses from one coil to the other. The entire mechanism by which a transformer functions simply does not operate, because the mechanism requires change and DC provides none. But that is only the first failure. The second failure is the one that kills it. When alternating current flows through the primary coil, something happens alongside the induction that most people never think about. The changing magnetic field created by the current fights back against the current that created it. This opposition is called inductive reactance, a form of electromagnetic resistance that exists only because the current is alternating and therefore always creating a changing field.